Okay, so now we're starting on section 2, which is talking about limits. And really it's not that hard for the most part. There are a few little tricky things. You can make it hard if you want to by doing little tricky things, but the reality is you don't need to, I guess, to prove that you fully understand it. You could do the tricky stuff, but to understand enough to do calculus well, you can, the more straightforward stuff is all you really need to know. Okay, so we're going to start with problem number 1. And this is, we've got a couple from here, I guess, a few problems from here. And basically what we do is we calculate the value of the function as you approach a number. You don't actually equal the number, but you approach the number. So if you look at problem number 1 and you look at the table, and I'll go ahead and make the table up here. So we're just going to have, let's see, how many elements? 6 elements, 6 by 2. Okay, so there's our table. And so what you have is the values of x, which are going to be in this row. So you can see we go 1.9, 1.99, 1.999. Actually, I need one more entry. But, okay, so let me start over again here. Make it a little bit bigger. Need one more thing. 7, 2 by 7, there we go. Okay, so again, values of x, this is f of x. So we have 1.9, 0.999. So you can see we're approaching 2, but we never actually equal 2. And then you go on the other side, and you can go close the same distance here, 0.001 from 2. You get 2.01, 2.01, 2.1. And the value of the function. So all you have to do is plug it in. Now, let's look at the expression. The limit as x approaches 2 of x minus 2 divided by x squared minus x minus 2. You say, well, can I just plug it in there? Let's do that. What is f of 2? This is a function. So what we're doing is we're taking the limit of f of x as x approaches 2. So if you did f of 2, you'd get 2 minus 2 divided by 2 squared minus 2 minus 2, which 2 minus 2 is 0, and 4 minus 2 minus 2 is 0. So what you get is what we call an indeterminate result, because it's 0 divided by 0. So the function does not exist at f equals 2, but it does exist, as we'll find out, as we let x approach 2. The question is, does it approach the same number if you come from less than 2 or greater than 2? So, let's put that in our calculator. So we're going to have, turn on, so we'll get 1.9. I'm going to put 1.900, so I can go back later and just plug in the extra decimals. So 1.900 minus 2, and I need to put some parentheses around it so I can keep the numerator and the denominator. So I have left parenthesis 1.900 minus 2 divided by the quantity. So it's 1.900 squared minus 1.900 minus 2. Okay, so that's the function at x equals 1.9. Make sure I did all this right. And so the number I get is 0.345. Okay, now I'm going to go back and then substitute, put another 9 in there, so I'll get 1.99 minus 2 divided by 1.99 squared minus 1.99 minus 2. I push enter, and I get 0.334. And then I go back and do the same thing, but I substitute in for I get 1.999 for all of those. When I do that, I get 0.333. Okay, now we go back and put in 2.01, 2.001, sorry, 2.001, 2.001, and I get 0.333. Substituting in 2.10, 2.010, I get 0.332, and finally putting in the largest number, which would be 2.100, 2.100, 2.100, push that in, and I get 0.323. Okay, and then you can use the graphing utility, which is basically plotting it on a calculator. I'm going to introduce you to the graphing thing that I'm going to use. But anyway, you can see that it approaches 0.3333. It's going to, the answer, the actual limit, the exact limit is 0.333 with a bar over top to indicate that it's going on forever. So let me minimize this for a second. All right, your screen's gone blank, and I just need to find my graphing program, which you can find in Blackboard. So let me share, stop sharing that, start sharing the calculator. Okay, so here it is. So this is the graphing utility that I want you to use just because it's free and it's easy. So if you look to the left, you'll see the function. So that's where you click on the upper left corner function and you put in the function. So the function that we're taking the limit is x minus 2 divided by x squared minus 2 minus x minus 2. So that's a function. And we're going to show it between, we're looking for the limit at x equals 2. So let's show the function. You can set the limits for the x and y values. And I'm going to go from x equals 1 to x equals 3, because we're looking at x equals 2. And then you say graph. So there it is. So that's the function. And if you look at x equals 2, it looks like there's a value there, but in reality, exactly at x equals 2, the function is undefined. And if I zoomed in on this, you can see it looks like it, but because the graphing program can't show the non-existence of just one point, it's going to do that. And you can see, if I take my cursor, it shows the x and y values, and so at x equals 2, the y value is equal to 0.33. But as we saw just a second ago, the actual function does not exist mathematically, because if you plug that in, you get 0 divided by 0. So that's, we can do, when somebody says, look for the limit numerically. Numerically means you pick numbers really close to the x value of interest, and then you plug them in very close to that, and you should approach some value. If the limit exists, it should approach the same value from both sides, from below and above in terms of numerical ranking. If we say determine it graphically, then you plot it on the graph and you look to see what the value is, if it exists. The ultimate goal is to be able to do it analytically, where we come up with a way of determining it exactly, rather than doing it. These are all approximate graphically, and numerically are an approximation. We can get pretty darn close, but you know, it doesn't give us the exact answer. Okay, this is problem number 5, chapter 1, section 2. And what we're asked to do is we're asked to numerically determine the limit of this expression. So the first thing we're going to do, which is what we should get in the habit of doing, is just checking to see whether it's indeterminate or not. If it's not indeterminate, we just plug the number in. So what you can see is if we stick 3 in for x, we'll get 1/4 minus 1/4. So the numerator goes to 0. And 3 minus 3 in the denominator is 0. So it's indeterminate. So to numerically determine the limit, we're going to just do what we did last time. So we'll make up this table. And we'll just plug it into our calculator. And again, the easiest thing to do is to set your calculator up so instead of having 2.9, you have 2.900. So I'm going to enter this in my calculator so you can do the same thing. So we have 1 divided by 2.900 plus 1 minus 1/4. The whole thing divided by the quantity. So when I say quantity, we put parentheses. So we have 2.900 minus 3. And I think that's correct. And so let me just write these numbers in. So I have 2.900. We have negative 0.064. Okay, we'll go second enter to get the equation back, and we'll just put 2.990 in there. Push enter, and we get negative 0.626. So that's 2.99, and then we have 2.999. So we plug that in. Push enter, and we get negative 0.0625. Okay, so it looks like it's approaching negative 0.065. And then we can go on the other side. And so we have 3.001, 3.10, 3.01, 3.10. Okay, so let's plug those in. And those should approach the same number if their limit exists. 3.001, 3.001, enter. So you end up with, let me put this on one page because it's hard to write that small. So we have negative 0.0624. So you can see it's on the other side of the limit. And then we put in 3.01, 0.010, and we get negative 0.0623, and then we enter 3.100, 3.100, and we end up with negative 0.061. So what we can see is that hold on a second. Oh, my cursor's not responding. There it does now. So the actual limit is probably negative 0.0625. So that's how you would do it numerically. And we're going to do the same thing graphically. So let me open up my graphing program, which I forgot to do. Okay, so let me stop sharing the, and I'll start sharing the graphing program. So again, you go over to this function, f of x equals over here, and you enter the equation. And it's fairly forgiving as far as, sometimes you don't have to put a plus sign in there. multiplication signs. So let's see, x plus 1, okay, minus 1/4 divided by x minus 3. And we're looking at x equals 3. So let's go from x equals 2 to x equals 4, and we graph it. Okay, so you can see it's at x equals 3. It looks like something's happening there, but in reality it's non-existent right at that point, and you can see the value y equals negative 0.064. So you can see that it's, if I zoom in even closer, I'll probably get a closer approximation. So 0.6. Yeah, I'm trying to center that exactly. Anyway, you can see it's negative 0.0625. And just go back to the expression. So all we're doing is plugging in our calculator into the equation, giving the values. We can see that whether you approach from the left, meaning the lower side, or the higher side, you're going to approach negative 0.625. Okay, the next 7 problems I'm just going to do one time because they're not that long. So all you have to do is just look at the graph and determine whether, if you approach the value of x from the left-hand side or the right-hand side of the number of interest, then you're going to get the same value. What I'm going to do actually is I'm going to stop here for a second. So what I'm going to do is actually I'm going to open up the book. So here is the book, and it's in the PDF version. So we're just looking at the limits. So let's just look at problem number 9 here. So we have a line, y equals 4 minus x. And they're asking for the limit as x approaches 3. So you see it's just a straight line. And so the value of the function is the limit. So if you plug 3 in, you'd have 4 minus 3. And what this dot represents is it's signifying that the function exists at this point. Now if there was a circle, an empty circle, then the function would exist everywhere except at that point. We'll see that later. Okay, problem number 10, the limit, again, because the function is continuous and it has a dot here at x equals 1, we know the function exists. So the dot's just to emphasize, this plotted y equals x squared plus 2 is this curve. The dot there is just to represent what's happening here at x equals 1. It means it exists, and so the answer would be 3. Okay, problem number 11, you've got this piecewise continuous thing, or piecewise function. So it says that at every point except x equals 2, it's this, and at x equals 2, it's 0. So if you look down at the graph, you'll see that it's a straight line, and there's at x equals 2, y equals 0, and the function does not, well, the function exists at x equals 2, but it's not, this function is not continuous because you can't just take your pen and keep it down. You have to lift your pen, go like that, and then go back up again. Likewise with this, it's showing that the function is the same as this, except at x equals 1, where it's actually down here. So what's happening is the limit still exists here, and this limit still exists here, because whether you approach it from the left or the right-hand side, you're still coming to the same point. So the function does not have to exist at a point for it to have a limit. It just has to be approaching the same value from either left or right. So that's true in both of those cases. So the limit is going to be the same. The limit here is going to be y equals 2. The limit of the function as x approaches 2 is y equals 2. And the limit of the function here as x approaches 1 is going to be 3, even though the function is not equal to 3. Here we have this absolute value thing, which we'll see. And because when x equals 5, you get 0 divided by 0, it's indeterminate. But in this case, because you get this jump, the limit as you approach from this direction is 1, and the limit as you approach this direction is negative 1. So we say that the limit does not exist at this particular point. It turns out that the function does not exist here either. Number 14, you've got a vertical asymptote. So again, the function does not exist because you divide by 0 when x equals 3. So the function does not exist, and the limit does not exist because as you approach from the positive side, or the greater side of 3, x equals 3, it goes to infinity. And when you go from the negative side of 3, it goes to negative infinity. So again, it doesn't approach the same number, and so the limit does not exist. Here we have a sine function. You're looking for the limit as x approaches 1, and again, just like the first two examples, the limit exists. It is the value of the function, and the same with this one. This is the function. At x equals 0, the function exists, and it is the same as the limit. When you come to 17, actually you're not doing 17, but I'll go ahead and mention it. The limit as x goes to 0 does not exist because what happens with this function is it just starts oscillating quicker and quicker and quicker. You probably might have remember seeing that pre-calculus. So the limit does not exist. The function does not exist either because you have 1 divided by 0, which is infinity. So the cosine of infinity, since cosine continually varies, there is no value in infinity. And here at pi over 2, it's just like this one up here. You just got a different way of approaching an asymptote. This is because of the trigonometric function. So the limit does not exist. The function does not exist there. Okay, so we're going to continue on here. So this is, we have problems 25 and 26, so we'll do this together. So what we're given in this particular case is to sketch a graph of a function f that satisfies the given values. And it says there are many correct answers, so I'm just going to show you one of them. You might, if you want to try it, come up with another one that might have the same characteristics. So I have my x and y axis, and let's just read through them. So the first condition is that f of 1, which I can see here, f of 0 is undefined, so the function does not exist. The limit as f of x approaches 0 is 4, so the limit exists, but the function does not exist. F of 2 is equal to 6, and f of 3, f of x as x approaches 2 is 3. So let's let's plot those couple of points here. So we know that we want the limit as x approaches 0 to be 4. So this is what we're going to do, is we're going to put a little hole here. So the function does not exist at f of 0, but we want the thing to come in and hit that particular point. It says f of 2 is 6, so that's well, no, the limit, okay, we got that. F of 2 is 6, so that's up here. So that point is going to exist. And it says the limit as f of x approaches 2 is 3, so that's right here. Okay, so I'm just going to put a light dot there. So what we could do is one particular solution would be to draw a straight line through these 2 points. And what is the equation for this line? Well, let's see, what do we need? So this point here is 2 comma, let's see here. Actually, we could have a multiple number. No, that's 2 comma 3, right? So it's 2 comma 3. That's the limit. So I'm going to put a hole here, but the function exists. Here I just got a hole, so the function does not exist. So in both of these cases, what you're going to have, so anyway, let's write this down here. So we're going to have 2 comma 3 is that point, and this point is 0 comma 4. So if we were to figure out what the line is that goes between those 2 points, how would we do that? Well, we'd figure out the slope first. So the slope is y2 minus y1 over x2 minus x1. So one of them is going to be let's choose this as x2, so, and that'll be y2, so you get 3 minus 4 divided by 2 minus 2 minus 0. So you get negative 1/2. So the slope's negative 1/2. And then you would use the point slope of the linear equation to get the equation for the line. So this is the form where this is your point and that's your slope. So all we have to do is plug in one of those points. So I'm going to plug in x equals 0 because that makes it easier. So you get y minus y1, which is 4, is equal to the slope, negative 1/2, times x minus 0. x1 is 0. So then you finally get the answer. By is equal to negative 1/2 x plus 4. So that would be the equation for the line that has these 2 points. And you can see that the limit exists because as we approach this x equals 0 from the left and x equals 0 from the right, that you approach y equals 4. So the limit of this function, so f of x is this function. So we said y, but it's really f of x, same thing. So f of x is equal to negative 1/2 x plus 4. So you can see that the limit exists because even though the function does not exist at this point, when you come from the left and the right-hand side, it goes to the same point, which is 0, 4. Here, when x equals 2, again, the limit exists. The limit is y equals 3. In contrast to this case, the actual function does exist, but the function's value is 6 and not 3. So that would be one solution. I mean, you could draw a parabola that went through those. That would be fine. It's more complicated, but you could do it. And there are an infinite number of parabolas because you can define a line by 2 points, but you need 3 points to define a parabola exactly. So we could put any number of parabolas. We could, what else could we do? You know, you could go horizontally here, and then you could change the slope to something going like that, just as long as it went through these 2 points. So, you know, another solution would be, I'm going to just, you know, draw something. So another solution could be a parabola that, say, has that as a vertex that comes back down like that. So it would be the same thing. You still have these holes. You just have this filled in. So that's why you can get an infinite number of solutions in. Okay, so that's how those problems work. So what we're going to do is we're going to do the next problem. So let's write down. I'm going to go ahead and just write them down here. F of negative 2 equals 0. F of 2 is equal to 0. The limit as x approaches negative 2 of f of x is 0. So in this case, the function does equal the value at, the function does exist at this point, and it is also the limit. And it says the second limit case is the limit as x approaches positive 2, f of x does not exist. So there's a couple of ways you can make it not exist. You could have a vertical asymptote. You could just say it's not, doesn't exist at that point. So I think I'll look at both of those cases. And again, there are an infinite number of points. So what we can say is that I should have extended this thing out. Let's move that over there. So there's negative 1, negative 2, positive 1, positive 2, 0, 1, 2. Okay, so f of negative 2 is 0, and the limit is also true. Okay, I'm just going to draw a line in the arbitrary line that goes through here. And then you could just have a straight line and then put a hole here. But actually, the limit does exist there. So how would I make that so it doesn't exist? Well, let's say I want a straight line to this point, and then I put in this other horizontal line. So does it satisfy the requirements? Well, f of negative 2 is 0. the limit as the function, which is this line for this part of the thing. We can figure out what the equation is. The limit is 0 because it fits right in with that straight line. Here, f of 2, sorry. Let's do that. So I'm just going to keep continuing up here as a straight line, and then we'll do that. Okay. I could put a little dot here. So f of 2 is 0 because there's a point there. These lines don't interfere with that being 0, but the limit here does not exist because when I come from here from the left-hand side, this is the value it approaches. If I come here from the left-hand side, this is the limit. But there's no, that's not a consistent limit in the function, but the function does exist. So again, I could do all kinds of crazy things here. I could have a, parabola that came up and came back down to here, and then drew this up there. So we had that, that point defined, but then you bounce up here. And you would use piecewise type functions, where you'd say from x equals -infinity to +2, it's a straight line, and from greater than +2, then it's a horizontal line. Okay, we're going on to problems 49 and 50. So let's just read what it asks. It says, use a graphing utility to graph the function and estimate the limit if it exists. What is the domain of the function? And can you detect any possible error in determining the domain of the function solely by analyzing the graph generated by a graphing utility? So what I'm going to do actually is I'm going to switch to the graphing utility. So here's the graphing utility. It still has the equation from the last problem, but the function that we have here is the square root of x plus 5, close parenthesis, minus 3, close parenthesis again, so everything's in the numerator. I have the x minus 4, and that's it. And I'm going to change the limits here because we zoomed in. I'm going to graph it, and then I'm going to just, if you push this button here that says standard, that'll make it go to the standard size, which is 5 by 6, I think. Okay, so what we're looking for is the limit as x approaches 4. And you can see there's some little weird thing going on right here. But if I zoom in on it, the weird thing disappears. Okay, so if I keep zooming in at x equals 4, which I guess I shouldn't have done there. How do I get back here? Let me go back to here again. So you can see as I zoom in at 4, you never see a discontinuity. The function looks like it exists, and that's because it only does not exist at x equals 4, and therefore you don't see it because you can't see a point in reality because it has no width. So that's the problem. So if you tried, the domain in this case is actually just two things in the domain. There is the fact that the equation, if you look at equation 49, is that you can't have a negative square root. So you look at the graph and only numbers of x greater than -5 work, because if you had a number less than -5, more negative, then you would end up with a negative square root. So that's why this starts here. But there's also this discontinuity at x equals 4 because you end up being indeterminate. The numerator will end up being the square root of 9 minus 3, which is 0, and 4 minus 4 is 0 in the denominator. So it's indeterminate, but you can't tell that from a graphing utility. So that's why we have to learn how to do this analytically. Again, we can do it graphically. We know it. We know the limit exists, but we don't know from the graph. We don't know that there's a discontinuity there, and that the function does not exist in the domain. It goes up to -4, but does not include 4, and then goes greater than 4. Okay, so that's the basic idea on 49. You can do the same thing on 50, so I'm just going to keep that open. And so 50 is x minus 3 divided by x squared. So this is one of these rational functions, and what you find out is that if you factor the denominator, you get x minus 3 and x minus 4, and the x minus 3's cancel out. So you might think you had a vertical asymptote at x equals negative 3. I mean x equals positive 3, but you don't. Okay, so I graphed it, but I put standard. So you do get a vertical asymptote at x equals 4. I mean at x equals 1, because that's the other factor in the denominator. So you just write it down here so you can see. So, you know, if we factor let me do that. Okay, if we factor the denominator again, it's going to be quantity x minus 3 times the quantity x minus 1, and the x minus 3's cancel out. So at x equals 3, it shows that it looks like it's continuous, but it really isn't. If we were to draw the graph, we put a little circle, open circle right there. And okay, so that's pretty much it.